So, who is here for the first time? I mean, who is like attending Speck&Tech for the first time? Raise your hand. Don't be shy. Okay.
Not that many, some
Yeah.
10, 15 people.
And so, we are a community of people who loves talking about technologies. And we started our community in 2016 here at Impact Hub. This is a picture from one of our first events. We were like 40, 30 people.
Yeah, 40 people.
Kind of. And we grew up. We had the possibility to have speakers from all around the world. Here, this is a picture from the 2019. There is the city of Cloudflare. We were like 100 people, so the room was pretty crowded. Until we reached the last Speck&Tech event. We were 300 people in a room. The event was done in collaboration with Dizzy, and we had the Professor Tannebaum speaking for us, which was super cool. It was a great event.
Who was there last month? Who was there? Can you raise your hands?
Did you enjoy it? Was it cool, right? I mean, and yeah, after the talk, we usually have a networking part where we can drink some beer, eating some snacks, and talk about what we have listened during the event. And yeah, as a Speck&Tech, we do not only organize monthly talk. From the last year, we started 2 new branches from the core of Speck&Tech. One is Speck&Track. So this kind of event basically is sort of a hike, a trekking around our mountains. And where there is a light talk, usually in a rifugio or a bivacco, where there are some foods. We talk about some topic related to technologies. Maybe there is some guest that is expert about some topic, and we spend the day together. We are super committed to this. Like, we went also with the rain, so we strongly believe in Speck&Track.
Incredible guys.
Yeah. And the other things that we started last year was alfabetizzazione digitale per gli anziani. So basically, we did 3 lessons with Fondazione De Marchi, where we help people that are not used to nowadays technology. We did 3 lessons. We had like 40, 50 students. The average age of the people was not the same as this room, but it was a super interesting event. Also a little bit challenging, you know, because you do not know what they know about technology, so it was pretty fun. And other small things. Like as a community, we gifted some leftover community to some people from the community of Speck&Tech. If you are in our Telegram channel, maybe you have filled a form to receive one of those. And also we had a draft where we selected 2 people from the community who attended the last PyCon that ended this Sunday. And yeah, so tonight is Speck&Tech number 53. A big applause. The name of the event is Throughput. The first speaker of the night is ALBERTO CHIUSOLE, right there. A big applause for him. And the second speaker is Simone Morandini.
Okay, as always, I'm gonna be the boring one, and after the 2 talks, there's gonna be a big part of networking with Beers and Speck. And you see these people here having fun, and of course enjoying the beers from Forst, our very local brand. There is a way for you to support our community, as you might be aware. First, if you noticed, we have these crazy T-shirts that resemble something that Speck&Tech has become in the past years. So not only tech, but also helping other people that are not our age, you would say, older people, and also going around in the mountains. So we try to put together these 3 cores of Speck&Tech into this T-shirt. It's a nice way for you also to, I mean, how many people can say that have your grandpa on a T-shirt? Yeah. So it's quite unique. If you want to buy it, it is 15 euros, and it also supports the association, and you're done with the donation for tonight. Second, if you still want to donate, you can go and get our beautiful stickers, swag, and if you're sitting on a chair, there's some swag from Mix as well tonight, so thanks a lot for that. You can donate in any way you like, also via SumUp, via payment, via card, via Satispay, everything you like. If you want to stay tuned on what we do at Speck&Tech, there is our website on speck&tech. It is quite interesting because you find all the talks that we were given in the past. It's over 100 talks. If you're studying for an exam, it may be also useful for you, if you're a student, to go there and find the slides or the speakers or get in touch with the professor, etc. If you're looking for a job, there's also a job board. Here, there are also some job opportunities from the Trentino Sviluppo that cherry picks, goes around the companies that are based in Trentino and select those that are into the tech environment. And it's quite interesting if you look at that, because it's not only like front-end developer, full-stack developer, service designer, whatever. It's service automation engineer, field service engineer, computer vision engineer. So jobs that are in the tech environment, but not exactly related to coding as you would expect. You can stay tuned on our channel. If you go onto our YouTube channel, you can find basically all the recordings of the previous Speck&Techs and the talks from the speakers. And it's very important, but at the end of the night, we will always send you a feedback form to tell you how the event was. It seems stupid, it takes 1 minute, but then we read every single question. And one of the feedback that we got in the past event was that it was kind of messy when we were putting out the chairs, if you're aware of that. So this time we have a beautiful REST API documentation telling you how to restore the chairs at the end of the night. Good job, Nicola. Good job, Nicola, for that. We will show this later when we need to tell you how to get your chair. Okay, last 2 warnings before kicking off the night. First one, we already have the next event that is going to be on the 27th of June. You'll be around for sure because the day before it's a holiday in Trento because it's San Vigilio. And what is cool about San Vigilio is that there's going to be the fireworks. So you have no excuses. It's probably the best fireworks you will see in Italy, I would say, quite easily. It's 25 minutes to half an hour of fireworks. It's insane. So try to be around and the next day come to Speck&Tech because we are going to be talking about wood and Industry 4.0. Second, this is an announcement that might be interesting for many of the faces I see in the room. We already have the dates for the next Speck&Tech retreat. The V4 is going to happen from the 6th to the 8th of October, so the first weekend of October. And it's going to be, again, in the beautiful Val di Sole. I'm not going to tell you this time what the Speck&Tech retreat is about. You can just go on our channels and see it. It's insane. It's just a very great weekend full of friends and people, sauna, spa, good food, workshops, talks at an insane cheap price. So we very recommend it. That's it? Yeah. I think we can start.
Yeah.
Last warning for the night. This is your code, slide.do/spec53, or you can just go to Slido and just type spec53, so you can upvote the questions or ask questions to the speakers. Ready for the night? Alberto, on stage. Welcome.
Okay. Hello, everybody. My name is ALBERTO CHIUSOLE. Tonight I'm going to show you a couple of slides about file system, special file system because it's a 35 petabyte file system, which is deployed. It's currently running in a Berkeley lab. It's a federal lab in the US in California, where I've been working, where I worked for a couple of years from 2020 to December 2022, before moving back to Trentino. Yeah, so let's dive in. So first, I wanted to show you how I ended up working in California. And this is a bit of my career so far. So I studied in Trento for my bachelor degree. I had a brief semester in Copenhagen before moving to Trieste for my bachelor and master. Sorry, for my master's degree and also to work with a company with which I did my bachelor degree thesis. And then I stayed there, continued working with them while I was studying there. And there I had the opportunity to visit CERN in Geneva, where and I spent a couple of months at CERN comparing file systems. So there was a file system at CERN, a Ceph file system, and I compared that to Lustre file system, the standard for high-performance computing, and we'll see more later. Then I moved to California at the end of 2020 to work at Berkeley Lab, which is one of the dozen federal labs in the US. It's a mix of different kind of, all kinds of science, but I was working for NERSC, which is the National Energy Research Scientific Computing Center, a big name for a data center specialized for high-performance computing. Then in December, I moved back to Trentino, and now I'm working for Sequera Labs, a company in Barcelona, where I'm the HPC DevOps engineer. Yeah, that's basically my experience so far. So what is high-performance computing? High-performance computing, or supercomputers in general, are used to run parallel applications that solve complex problems, such as, I don't know, nuclear physics, astrophysics, molecular design. They also use them for COVID vaccines to do protein folding for the COVID vaccines. HPC is a bit different from grid computing. There are things like home, I don't remember the name right now, but basically grid computing, you can split a problem on different computers. You can run a portion of that problem on your laptop and contribute to the project. While HPC, high-performance computing, needs a tightly coupled system, so you cannot spread your work across the world and just put it together at the end. So it's a bit more complex, and it's used to solve complex problems too. As you may imagine, it's an extremely expensive setup. And certain labs are also a matter of national security because they deal with nuclear warheads, stuff like that. So they have people with machine guns at the entrance. So not the funniest place to be when you're not invited. So tonight I'm going to show you, introduce you to Perlmutter, which is this supercomputer that was installed in 2021, 2022 at NERSC. And this is just the front row. Imagine like 5 more rows like these. These are like racks, so they're probably as big, bigger than me, like 2-3 meters probably tall, times 5. And this is just the compute power. Then there is the file system, which is what I was working on. But yeah, so this is the beast that I will show you tonight. This is called Perlmutter because it's named after Saul Perlmutter, which he won the Nobel Prize in 2011 for his 1988 discovery that the universe is expanding. And he was able to win this Nobel Prize also because he managed to run simulations on supercomputers. In 1988, there were like smaller or less powerful supercomputers, but at the time he used them, and he was able to win this Nobel Prize for his discovery along with his team. So this is the landscape that we have inside a HPC data center. So we have the compute power, like the horsepowers are here, and the Perlmutter system as a mix of CPU-only nodes and GPU nodes. Like there are 4 GPUs per each blade. That's the name of the server. And then there are the file systems. There is one. This is the Scratch file system, the fastest one. Then there's the community file system, like the mid-term file system for medium time scale files, so files that need to stay around for a couple of months. There are also much longer term file system, like tape, like actual tape, like a VHS tape, basically. Then there are like gateway nodes, routers, and there are also external facilities that are connected directly to this facility. And all of this is connected through a powerful network. And this is the most important part in an HPC center. The network is definitely the most important part. Yeah, it's a 200 gigabit per second network. Well, I won't bore you with all the details, but yeah. Yeah, so I don't know if I'm allowed to say the whole numbers, but let's say this is in a ballpark. This is like around 100 million, probably more, dollars. So yeah, they go to Washington and they get a big check. They carry it back to California and they get this beast here after a couple of years. It's a convoluted process because they need to talk to vendors and negotiate and get the best deal, and then that's it. Then they get these computers. So here's the back of a compute cabinet, and you can see blue and red pipes are for the liquid cooling, and because these machines they can get so they can get so hot that they need to be liquid cooled. So there is the first cabinet. You can get a glimpse here at the end of the row. The first cabinet is just a big boiler, basically a reverse boiler. It's taking the heat out and pushing it out to the vents outside. Funny thing, there are some special tiles here because this is in California. As you may know, they're still waiting for the big one. So all the floor of the data center is installed on top of special tiles that are meant to break in the event during an earthquake. So these tiles are meant to break, and and below the data center there are like massive wheels that are holding all these tons of steel on top. So the idea is that the racks are going to stay still while the whole building is moving below it. So yeah, they're thinking ahead, let's say. Yeah, so the hardware, as I said, is made of all these racks of blades. These are special servers. They are not like pizza box units. There are blades. You can pull them out and plug them in. You don't need to untouch cables. There are like sockets ready for the blades to be inserted. So to speed up management, because every minute that a node like this is out of system, is a minute that it cannot compute. And after a certain amount of nodes that are out of the system, they start getting calls from Washington asking, why is my $100 million system down for so long? So yeah, it's a part of the game. So yeah, as I said, there are CPU, GPU nodes, and now we're also starting to see FPGA nodes, so field programmable gate arrays, highly specialized hardware. But as I said, the masterpiece here is the interconnect, so the network, and here is a slingshot system built by. It's a proprietary system built by HPE, based on a mix of copper and fiber, using both Ethernet and InfiniBand protocols. But why are they using these? Because the reaching a single-digit microsecond is crucial, and we'll see why. So this is optimized for HPC. There is much of the protocol is offloaded into the silicon. Yeah, as I said, there is a mix of Ethernet and InfiniBand. InfiniBand is cheaper comparing by the same performance. As I said, there are liquid-cooled units, so you can see the colored pipes, and they can get quite hot. I can trust me. Yeah, funny thing is that one of the first incidents was that the liquid that was used was not sterilized. So basically, we started growing some bacteria. So yeah, a supercomputer had an infection, but not from a virus, like a computer virus, but from a real virus or bacteria. So yeah, that thing can happen. Yeah, and then obviously there are file systems because you cannot just compute. You need something to compute on. So yeah, there are different tiers of file systems, as we'll see. Yeah, so the software landscape. So we saw the hardware, and now the software is Linux only. It's a Linux only world for supercomputers. So I invite you to visit that link. It's the top 500. It's a list that is created twice a year. One for each conference. There is a European conference and an American conference about supercomputing, and you can see crazy stats there, and I'll show you some later. But yeah, so the idea is that HPC is made for parallel programming. You don't go there and run your Hello World or your Python code. Well, you can run some Python code, but we'll see. The OpenMP is the deal for intra-node communication. Then you have MPI for extra node. And may sound as a surprise, but you can basically see Fortran everywhere. And Fortran is like he's probably older than my father, but yeah, still around in HPC, and we probably won't see the end of Fortran anytime soon in HPC, because it's made for numerical stuff, and that's its job, and it's doing it just fine. So rarely you see some C, C++. Now we're starting to see some Python. It's gaining some traction, especially for data analysis and for machine learning, and that's the reason why we have all those GPU nodes as well. And then there are job schedulers, things like Slurm, which is the most popular, which allow the user to request a certain number of nodes. You can SSH to a supercomputer and ask, I want to run my numerical fluidodynamics code on 100 nodes, and the system, the job scheduler, will reserve part of the supercomputer for you to run your code. And that's the way that the system is able to allocate resources for any user. So basically, you end up in a queue, and your job may run in a couple of minutes, hours, days, sometimes if you're asking for a big reservation. Yeah, some of the challenges in HPC are storage, for sure, I/O and data transfer. So moving data, and we'll see more about this soon, is one of the hardest part. You want to write the least, and you want to move the least amount of data as possible. Also because you need to keep the data local to the node, if possible. Some numbers that, so I was talking about power usage before. Per mother, this system is running at, when running at full power, is running at 2.5 megawatts, while the Fugaku, like the most powerful or the largest supercomputer, runs at 29 megawatts. So 2.5 megawatt is like 830 households at full power. Like if you divide this by this, you get this number. So imagine running a neighborhood, cutting the power from a neighborhood to run a supercomputer. That's basically the deal. And you can do the math for this is even crazier. I hear that like people that when they need to run these supercomputers are high capacity. They call the local energy company and they say ramp up the production because we need some more power now. And obviously, cooling, as you may expect, is also another important factor in supercomputers. The location of the data center is important. And Berkeley Lab, the location where Perlmutter is installed, benefits from the cool temperature of the Bay Area, which is, I guarantee you, is not almost never above 20 degrees Celsius overall over the year, which is great for data centers and for humans too. And that's also a reason why you cannot place data centers in deserts, because you need water to cool the temperature inside the building. So moving into I/O, which is what I was working on. So I/O is input-output, so everything that works with data and storage. At a large scale, you cannot expect to have a single disk running your computer to store all of your data. And so you end up using multiple servers, multiple disks, drives, and you end up with some funny problems like synchronization, consistency issues, like when two processes are writing to the same file on a distributed file system. You need to have something to guarantee consistency, some kind of consistency, let's say. And optimizing I/O is also crucial. One reason why I was saying that storage is one of the most important part is because CPU, so computing, runs at, so you have your CPUs running at gigahertz, which is like nanoseconds in period. But while the network or the NVMe drives work at microseconds. So it's a 3 orders of magnitude slower than compute. So you want to keep your data inside your node as much as possible. That is the idea. And reducing all these input-output, all these network phase improves the overall compute capacity, or sorry, compute hold time by a lot. So that is one problem. At NERSC, there are several layers of file systems. So you can have the memory layer, so keep your data all inside your node. But sometimes you have multiple nodes, and you need to make them collaborate together. So you write to a file because you maybe are running or are operating or managing a terabyte large file, and you cannot store it in memory in a single node or keep a copy in each node. So you need several layers of file systems, and the most performant one is the Scratch file system, and then there are several other layers below it. So the upper you go, the more performance that you get from the file system, obviously, but the less capacity there is, and the lower you go, the more capacity there is. So there is a trade-off. Basically, this is what I was saying before. So the community file system runs on HDDs, so on hard disk drives, and you should store data that is used within the same month or a couple of months. While the archive data should be moved to tape, which is like VHS, like the one that you have at home with Harry Potter on it. It's like a VHS. And this is like the tape library that is installed at NERSC, and in all data centers, in all HPC data centers, there is a robot that goes around and flies back and forth, grabs a tape and puts it in a driver. And after a couple of minutes that you did your CP, copy file, you start to get your file after a while. So it's great because it's cheap. It's really cheap. It's not so great because it's very slow. So you cannot run your applications with data on tape. You need to first offload it into the upper layer, or even even the Scratch layer, and then start working on that. So moving on to the most interesting of this file system, the Perlmutter Scratch file system. Permatter, as far as we know, or as far as at the time at least, was the first all-flash file system. So the first file system running only on SSD drives. And it was composed of 3,000 Samsung NVMe drives, like these. These are exactly the same model, of 15 terabytes each. Yeah, there are some very interesting numbers. You can probably run a couple of games of Minesweep on these, or pinball, and it gets really fast. Yeah, so it's a 35 petabyte of usable POSIX storage, because if you compute the math, if you multiply the number of drives by the capacity of each drive, you get a much larger drive, a much larger overall capacity, but you need to take into account replication, so you need to keep somehow multiple copies of your data, or some kind of parity to recover your data in case of a cabinet crash or enclosure failure. So yeah, this is directly integrated into that big giant network that uses the proprietary fiber and copper mix. Yeah, and fun fact, this is enough to back up the Lord of the Rings a couple of million times. Or if you're a big fan, you can back up 150 times the extended 4K version of The Lord of the Rings. Yeah, so this is how a rack looks like for a file system. You have switches on top, there are gateway nodes, and then there are metadata and object storage servers under it. Each one of these probably is not really readable from this, or is not really, you cannot appreciate it, but every one of these is a drive. So there are like already hundreds of drives here. There are two components. One is a metadata server, and one is an object storage server. On Permatter, there are 16 metadata servers, so this is considered one metadata server, 1, 2, 3. So there are like a couple of racks only dedicated to metadata, and then a bunch of other racks dedicated to the actual storage. So every time you do an LS on a supercomputer, you're hitting first the metadata server, which tells you what is the directory. What is the directory structure? What are the file names that are stored in that directory? Where on the inode table are the objects stored? The objects stored inside the object storage servers. You can also decide the file layout, which is important for HPC. So you can tell it the file system, okay, put a certain amount of megabytes on one OST, the next one on the one next to the first. So you can, when you fetch data, when you ask for your data, multiple drives are able to serve your data at the same time. So you get an aggregated, much higher performance than just storing everything in a single drive. So inside each one of these 2U units, there are actually two servers, two twin servers, each one with its own power unit. Then there is a mid-plane for interconnection. And on the front, there are like 24 NVMe drives, the one that I showed you before. And each server inside has direct access to the first half of the drives, but can also take over the other half if needed. So if, let's say, the power unit of the second server goes off, or the first server can also take over the other half of the drives, so it's able to provide you with access to your data, even in case of a failure of a single server. The file system, so inside these drives, there are other file systems. So there is a big file system that controls other file systems. It gets convoluted, I know. And there are several layers of RAID involved. So there is a 8+2+1 RAID 6 with a, so it's a, there are two 2 extra copies of your data out of 8 plus 1 of parity, and then another RAID 10 for the metadata servers. Yeah, so each one of these servers is able to deal with 128 PCIe Gen 4 lanes. Yeah, and this is a switchless design because every unit here doesn't have a switch inside. The switch is only at the rack level, and then there are like dozens of racks. So the switches connect only rack to rack, not disk to disk. Yeah, so going into the software that is used, MPI, as I said, is the bread and butter for multi-node communication. So everywhere you go, there is MPI. And MPI-IO is the component inside MPI that manages the I/O layer, like file pre-allocation, the offset management. So when multiple processes write into a file, usually the file is pre-allocated, and then each process writes at its own offset, and the file system is able to coordinate these writes into a single coherent file. Then there are other software like HDF5 they use MPI for the parallel I/O, and then there is NetCDF that uses HDF5 as a storage format. And yeah, NetCDF is usually used by climate science people because it's meant for a time-based access. So yeah, there is a bunch of software used, and the goal of a supercomputer is to support all of these. So during our performance evaluation of this file system, because we got the file system from a vendor, and we needed to check that the file system was working as expected, as promised, and we used a tool called IOR, which is a tool capable of generating synthetic I/O. So I/O on demand, only I/O, no compute, no network, only I/O to the disks. And we were able to benchmark the different components of our file system. So we were able to, using FIO, we were able to benchmark the NVMEs. So talking directly to the NVMEs, checking what is the performance that these NVMEs are capable of producing. And these are the numbers. So reading sequentially, you can get 42 gigabytes per second per NVMe drive, or 9,000, 9 million IOPS reading and 1 million and a half writing. And then moving on to the different elements. So there is a grid RAID, so testing how the different drives collaborate to create a single unit. And we were able to see that the performance was maintained throughout all the other layers. So there is also the LNet, so the Lustre network part, and finally IOR, which was the application layer. So we were able to see that the performance was almost maintained. There is a drawback here on the IOPS, which is the IOPS is the metadata. So every operation that you do, like a mkdir when you create a directory or you access the stats of a file, those are IOPS because they are small, incoherent operations. So every time you create a directory, you are writing a small file to the metadata servers, and there is a huge performance drop here caused by this read, modify, write, because the metadata servers are meant for large operations. So every time you do a 4K access to a file, you're accessing like the whole unit, which is like 128 kilobytes, and then reading, writing, and you get this penalty. So you get 5% or 15% if you're reading out of the IOPS from compared to the drive. Yeah. So testing things on this file system, we were able to see 1.5 million files created per second. So we were able to create this amount of files. And there are certain users that do this, like they go crazy and create small files. So we had to test this. In a full-scale run, instead, we were also able to see over 1 million files deletion per second, which is a very good amount. Compared to the previous file system, which is the Cori file system, because it was the file system for the Cori supercomputer, which was running on HDDs. This is a way smoother user experience. Sometimes we were getting tickets from user asking, is everything okay? I'm doing ls on my directory and it's returning after a minute, because sometimes they had like, I don't know, 10,000 files in a single directory, and that was crawling the hard disks. And this is definitely better. So if you cannot change your users, change your hardware underneath. And you probably problem solved, a couple of millions of dollars, but yeah. Some surprises that we saw. We discovered that the SSDs, we noticed that SSDs slow down with age. So after some number of writes, the SSDs slow down. This is like the HDD fragmentation, because you're basically writing bits here and there, and you're deleting them maybe, and then you're creating all these holes in your file system. And this causes the file system to split up or move your files, your chunks around. So we noticed a 10% reduction in write performance after 5 times of the capacity of a drive was written to disks. But FS stream was enough to fix it. And with some calculations, so calculating the 5 times the capacity of a disk and how many petabytes we're estimating to get per day, we estimated that every 60 to 80 days, a full FS stream was needed. But the longer you wait, the more work FS stream needs to do to fix and to reallocate your files. So we were performing this nightly, so even if it was probably an overkill, performing it nightly took like a couple of minutes, and the users didn't even notice. So this was something that we noticed. And that's it. Questions? Yeah, by the way, I use Fedora, not Arch.
Okay, thank you for the presentation. We have some questions for you. The first one, what do you reckon of the current valuation of NVIDIA? Are we entering in the golden era of supercomputing?
I never heard of NVIDIA before. This company never heard of it before. Okay. No, joking apart, I think probably there's a lot of hype around this, and also a lot of hype around the AI. I'm not an expert in AI, but I think probably we'll see the tech world move more into GPUs and more into specialized hardware. So NVIDIA and probably even more companies that are not just GPUs but also FPGAs may see a boost in interest.
Okay. Second question: is Rust ever used on high performance machine?
Yeah, like C, I guess. The point is that HPC is done by people that are probably, let's say that I was the younger in my work group by 20 years. So it's like a kind of a niche area, HPC. So getting something new into HPC is hard. As you can see, there is still Fortran around. So probably some new projects may start using Rust, but I haven't seen it much in HPC so far.
Yeah, also because Rust is pretty challenging as a programming language. So, okay. What is the impact of HPC infrastructure on the environment? Like, is there a chance to run on site with green energy alone?
Mm-hmm. yeah, of course, it's challenging, and of course you can buy energy from a green source, but you're taking that energy away from somebody else. Yeah, of course, it's part of the deal, and there is some research nowadays trying to estimate how much your research costs to the environment as part of your overall career. So every time you take an airplane to go to a conference to show your astrophysics results, there's also some energy used there, and some. So it's something that is being investigated, and we were able to monitor the energy usage by job. So users were actually able to get a certain kind of information. So how much energy did their job
So
take?
they know how much they are polluting the air.
How many kilowatt or kilowatt hour they were using. So yeah, you can estimate. But I don't. So in California, most of the energy comes from photovoltaic. Yeah,
Solar energy.
solar or wind, some nuclear, and also some oil. But yeah, the mix is variegated. But yeah, you can get certain data centers, like in Iceland. They run data centers with a geothermal energy, and they have like the cool air, so they don't need any big vents. So they're pushing a lot on clean energy, clean data centers in Iceland. The point is that it's kind of far away, so there's a lot of latency, and
this is not convenient.
Probably Simone will tell us more.
Okay. Last question for you. Which is the greatest challenge working on this project?
Probably wrapping your head around all of this mess. Took me a couple of months. Yeah, and then going to conferences and showing what I showed tonight, maybe in more detail, in front of like people that do this every day for the last 20 years. It's also very, very challenging, and yeah.
Okay.
Probably.
Thank you. A big applause for Alberto. And welcome on stage, Simone Morandini. A big applause also for him. Come on. The networking part after the presentation. So if you have any other questions, I mean, Alberto and Simone will be there, so you can talk with them.
It's okay, it's running. Okay. So good evening, everybody. My name is Simone Morandini, and the goal of this talk is to try and explain to you what happens behind the scenes of our everyday usage of the internet. It's pretty challenging to do it in half an hour, but I know that Speck&Tech people are quite smart, so I'll try to do my best and share the knowledge. But we will start off very easily because when we talk about mix, we talk about the internet that we experience every day. And so if you ever recognize yourselves in one of these scenarios, I'd say that you've already been at mix, maybe without even realizing it. And I'd say you've been here or there, depending on where I am when I give the talk. But when I say that you've been at Mix, I mean that you've been physically there. You know that when we watch a video on YouTube, we don't really care about where the video is located or the path that it travels to get to our device, because there's a cloud in the middle that do this for us, basically. Well, Mix is one of the places where the cloud dissolves, and it turns into routers, switches, and fiber cables. Where are we located? We are in the western part of Milan, close to the San Siro Stadium, inside a campus which is pretty famous for everyone working in the TLC industry. It's the campus of Via Caldera. It's so nice that we thought we dedicated a T-shirt to it as well. It's a place that it's almost unavoidable for people working in the IT industries because this is the place with the highest density in fiber interconnection that we have in Italy. And that's why Mix was born there as well. It's not a place that has been designed to be what it is today because it started off as a simple office space. But in the early 90s, something started to move because local operators that were geographically close started to experiment local interconnection because they had to use, up until that point, interconnections that were already made and that traveled throughout Europe or even back and forth from the States. That experiment in 1996, luckily for us, went well. And in 2000, 28 companies that at that time were the expression of the main internet companies working in Italy, they founded Mix. Those years has been pretty dynamic for TLC, so big fall, big growth, acquisitions. And so out of the 28 members, now we have 16 of them, but they divide the pie pretty evenly because the concept of neutrality was something that we wanted to give since the very beginning. This is just a couple of words to introduce the company, but my talk is and wants to be more technical. There's a quote that pretty much summarizes everything that I'm more or less going to talk about. So a name indicates what we seek, an address indicates where it is, and the route indicates how to get there. It's a quote from Mr. John Postel, who is a legend of the internet, an internet pioneer. And this is taken from the RFC 791, which described the internet protocol. So let's start off with the basic principle, IP addresses. You know we have IPv4 and IPv6 addresses, but the everyday usage on the internet, I mean, when we navigate, we rarely have to configure, to explicitly configure them, right? And I don't know if you ever managed how these addresses are actually managed globally and where the one that I'm using, why I'm using a specific IP address and not another one. So the solution, the approach to this problem is a hierarchical one. So we have a central body which is called IANA, which manages the entire addressing space. IANA divides the space into big chunks that are given to special entities that are called regional internet registries. And those RIRs then further divide the space into smaller space that is given to local operators, which then manages it autonomously. There are 5 RIRs in the world. So we have RIN for North America, LACNIC for Central and South America, AFRINIC for Africa, APNIC for Asia Pacific, and RIPE-NCC for Europe and Middle East. What's the scheme when distributing addresses? We have IANA, we have an RIR such as RIPE-NCC, for example, and IANA reserves a certain chunk of addresses to the RIRs, which then, in turn, gives a smaller piece of that addressing space to what we call ALIR. ALIR are every network operator that comes to mind. So Fastweb, Telecom Italia, TIM, Tiscali, all of those are ALIRs. If this notation is not, if this notation is not too familiar for you, maybe we can discuss it further because I don't have the time to go into much more detail on this, but just think of IANA as managing the entire world of chocolate bars. Every now and then, IANA gives a chocolate bar to the RIPE-NCC, and the RIPE-NCC breaks this chocolate bar into smaller pieces that are given to the LIRs. So this is the similitude, how it goes. These LIRs can have more assignments over time, and the set of these assignments form what we call an autonomous system. So an autonomous system is a collection of networks and routers that live inside the same house somehow. ASNs, autonomous system numbers, and LIRs are two different concepts, but for the sake of this presentation, we can safely assume they are synonyms. Autonomous systems are identified by a number, and that number is given by the RIPE-NCC as well, or equivalent RIR. So for every operator in Europe and Middle East, RIPE-NCC gives out IPv4, IPv6, and autonomous system numbers. So they do a pretty important job. And if you're curious to have a look at it yourself, this is the website of RIPE-NCC. There are tons of information over there. This one, the RIPE database, is one of the most useful tools for network operators because you can type in any IP address and any a number of autonomous systems, and the tool will tell you which is the legitimate holder of that resource. There's something that more or less every network engineer has been talking about over the last 5 years, which is IPv4 depletion, and I think you might all be aware of it. So believe it or not, IPv4 addresses are basically exhausted because the standard, the original standard, has been written in 1981, and at that time, more than 40 years ago, having more than 4 billion addresses available was science fiction. But nowadays, the resource, despite being large, is finite and it's almost exhausted. There has been new phenomena over the last years. So there has been limited assignments. There has been a huge effort in reclaiming a new space, and there is a pretty active IPv4 marketplace. But nonetheless, there are no catastrophes at the horizon because what actually needs to be done is just build an IPv6 network next to an IPv4 network. If you don't go into a router and physically remove the IPv4 address, there's no expiry date on them. So the effort actually is to build dual stack, what we call dual stack networks. This is a small timeline of what happens over the last year. So you saw it's a pretty recent phenomenon. And right now, if you are an LIR, you are no longer applying for a waiting list, but allocations are suspended because the RIPE-NCC board recently decided to stop accepting requests for the waiting list. Actually, there has been a vote last week on new charging scheme that might result in unblocking this decision, but right now that's the status of the art. So we have IPv4, IPv6 addresses living inside an autonomous system. And let's suppose these are the first two autonomous systems ever made. It would make sense to interconnect them, right? Because customers of either party can then talk to the other ones. And suppose that after a while, a new autonomous systems with cool movies comes up. So probably those two autonomous systems will then interconnect to that autonomous systems as well. But you may be aware that there are literally tens of thousands of autonomous systems in the world. And what are you supposed to do? Just interconnect everyone to everyone else? No, you don't do that, because it grows with the square of the nodes involved, and it rapidly becomes unmanageable. So what's an efficient way to exchange traffic then, to interconnect to one another? Is just have these autonomous systems connecting to a central space, to a central platform where they can easily reach all the others. MIX is an internet exchange point, and it's, again, a common place where autonomous systems can easily interconnect to other autonomous systems and exchange traffic. There's no hierarchy in this diagram. So all the ASNs here are basically peers to one another. And in fact, exchanging traffic via an autonomous system, via an internet exchange point, is called peering for this matter. From the topology point of view, Mix right now is more or less a simple Ethernet LAN. We have our switches here that build the physical infrastructure, and to those switches are connected the routers of our members. An important thing is that these objects here are property of Mix and are managed directly by us, while all the routers are property of our members. And they configure those devices, so we don't do that on their behalf. Want to see some of them in real life? This is a sample, this is an example of our peering switches that can go straight into your cable porn gallery, I would say. And on the other hand, we have routers of our members. So you can imagine that every fiber cable here is connected to another fiber cable to one of those devices over there. And who are the owners of these devices? Well, we have a bunch of subjects that are connected to Mix. This is just a sample of the more than 380 different autonomous systems connected to Mix. So Mix was born with the ISPs, basically, so the guys that bring connectivity to our homes and offices, and with carriers who build internet backbones. Then over time, we included cloud providers. We include content providers, who are the guys who has the content that we ask for. And there is another important category of members who are the CDNs. CDN stands for Content Delivery Network, and those are the guys that actually deliver the traffic to your device, to your tablet, to your smartphone, to your smart TV. So when we talk about Mix, and those are a few of the examples that I gave at the very beginning, you can think of being a customer of Eolo, downloading software updates for your Windows laptop. Or you can be an Iliad customer watching streams on Twitch or videos on TikTok. Or you could be a customer of Win3, updating your website hosted on Aruba. Or you can be any one of these guys just looking for the next perfect gift on Amazon. All of these subjects are connected to Mix, and Mix is one of the places, one of the alternatives that these operators have to exchange traffic among them. We have no way to enforce them, to oblige them to do so, so we provide the infrastructure, but how much and when to use that infrastructure is always up to the members. And what is the rules, what is the language that all these autonomous systems speak to each other? It's BGP. It's the Border Gateway Protocol. BGP is truly one of the pillars on which internet is built. And when we talk about BGP, we don't really go into details on how a network is built internally. We just see the network as an autonomous system number and a collection of networks that live inside that autonomous system. BGP is a language spoken between autonomous system by what we call BGP neighbors. And those neighbors happen to be on the edge of the network. And so they are the border gateway of that network, hence the name BGP, Border Gateway Protocol. Fun fact, BGP is also called the Three Napkins Protocol because the first two engineers were at lunch break at a meeting, and they had no better paper than a couple of napkins on which to sketch their ideas. Luckily for us, they transferred it on something more durable, so it reached our days as well. How actually BGP works, it can be described by this small scale model. So we have Mix at the center, and we have a bunch of autonomous systems directly connected to Mix. every one of these autonomous systems has its set of networks, and when a BGP session is established, then an autonomous system is said to announce its networks to his neighbors. So autonomous system 100 will send his 5 networks, so basically IPv4 and IPv6, I would say all at the same time, even if they are configured separately. Then 75 will do the same. 50 here has a customer, so he provides connectivity for 25. So in order for 25 to be visible by the other 2 guys, 50 has to announce it as well. So 50 will go on and announce all these networks to his 2 neighbors. At the end of this process, you see that on every router has been built what we called a routing table, which is a set of destinations which are reachable via those neighbors. Here you see everyone talking to one another, but bear in mind that BGP session must be bilateral peering agreement. So if only one of the 2 parties want to exchange traffic, then there's no BGP session coming up. If you are the manager of one of these routers, you can have multiple ways of see what the router has learned. And I'll just show you a couple of small commands. So you can ask the router to give a summary of the information he has. So you see the list of IPv4 network, the list, sorry, of the IP addresses of the neighbor, the autonomous system, and last column, the number of prefixes, the number of networks that are being received by the neighbor. And if you want to go into much more detail, you can ask the router to show exactly what are the networks that are being received by the neighbor. So in this case, you see all the 13 neighbors, all the 13 networks. You see the details here, and you have another very important parameter here, which is the AS path, the autonomous system path, which is the list of autonomous systems that needs to be crossed in order to get to that destination. This the scale model is complete, is correct from the BGP point of view. It's incomplete as a much broader approach because it was missing those dotted lines. Those dotted lines are a requirement to join mix because if ever something bad happens here, we don't want to be the cause for isolation of that autonomous system. So it's a requirement for any autonomous system joining mix to have connectivity which is independent from mix itself. Is it a fairy tale world where everything goes well? Of course it's not. So every now and then there's something that goes wrong. And I'll just show you a couple of examples of BGP incidents that go by the name of BGP hijack. So whenever a traffic is somehow being stolen from one party to another. This is a pretty famous example that happened between YouTube and Pakistan Telecom. So you see here a large number of numbers which are autonomous systems. This one is YouTube, that one is Pakistan Telecom. From the routing perspective, YouTube is announcing a specific /24, which is the part where our videos are located. It happened that a series of videos that the Pakistani authorities found offensive were uploaded to YouTube. So the order that was given to Pakistan Telecom was make YouTube inaccessible for Pakistani users. But what happened on the routing level was that Pakistan Telecom started announcing a network which was more specific. And from the BGP point of view, a more specific network, a smaller network, is preferable because it tends to be closer to the actual destination. And so the vast majority of routers throughout the world thought that that announcement was better. And they started sending traffic towards the network of Pakistan Telecom, where, of course, there was no YouTube video. All the requests just fell off into a black hole. Okay, that traffic was being diverted. That traffic was being hijacked from YouTube onto Pakistan Telecom. So they do not made YouTube inaccessible for Pakistani users. They made YouTube inaccessible for half of the world during those 2 hours. And of course, some some bells started to ring on YouTube, and so they started acting a countermeasure. Here it is. So what did they do? They started announcing the very same /24 that Pakistan Telecom was announcing. So the routers now had two identical announcements for the same /24. And what's the next criterion to be looked up? It's the length of the autonomous system path. So the shorter the AIS path, the better the announcement. So autonomous systems that were closer to YouTube started going back to the real YouTube. Autonomous systems that were closer to Pakistan Telecom stayed on Pakistan Telecom. What was the solution to that? Well, YouTube started announcing an even more specific route, and that got all the traffic back to the real source. This happened back in 2008. So a long time passed, but it was a milestone in networking because it had a very famous victim like YouTube. This other video that I'm showing here instead had Twitter as a victim, and this actually happened last year in 2022. So a lot of years passed, but still this incident occurs. Now you have, this one is Twitter, which is announcing a specific /24, which is the one that, behind which there's the Twitter that we know. This guy here, RTCom, is a Russian operator that's starting announcing the same prefix. So you see that a few autonomous systems, again, thought that was a better announcement, and they started sending traffic that was intended to go to Twitter to RTCom, where, again, there was nothing like Twitter. In this case, the event was much quicker because it only lasted 50 minutes instead of the 2 hours that the other case. So at a certain point, the announcement got dropped and everything went back to normal. So what's the message here? If you look it up as a fun fact, the very same prefix had the very same incident 1 year earlier. So in 2021 was hijacked by another company. But at that time, Twitter had not put in place security measure. So in 2021, the same incident took more than 3 hours to solve. In 2022, it only took 50 minutes to solve. So I cannot go into much more detail about this, but if you're interested, I don't know, take this slide as homework to read further on. RPKI is one of the most important initiatives that is being carried on by network operators. The idea is to secure announcement, to have a digital sign on resources so that you can run a validator software and be able to detect if an announcement is valid or not. So you can decide whether to accept it or discard it. So getting back to Mix, and I'm wrapping this up, a few traffic stats from us. This is an average day at Mix. We recently peaked at 2.38 terabits per second that are close to 10 petabytes of data every 24 hours. So nothing like you worked on, actually, but pretty decent numbers here as well. What's pretty fun is to see the shape of the traffic. So we have a minimum, which is always between 4 and 6 a.m. in the morning. Then we gradually wake up, we start working using the internet. We have our lunch break. Then we go on with the coffee in the afternoon. We have dinner, and after dinner, we'll turn on our Amazon Prime Video, our Netflix, our streaming service. We always have our daily peak between 9 and 10 p.m. in the evening. And those are numbers that continuously grow. This is the entire history of Mix in terms of annual traffic peak. So you see that over the last few years, we had a pretty steep increase. Of course, this is due to the difference in the interfaces being connected to our peering LAN. So You see there are no more fast Ethernet ports. We are selling no more 1 gigabit ports. The vast majority is 10 gigabit ports. More than 20% is 100 gigabit ports. And probably by the end of the year, we will be able to connect the first 400 gigabit ports. There are events. You know, the graph that I showed you before is an average day. There are events that drive traffic away somehow. You see that here there is a chunk of traffic missing. And I don't know if you have ideas of what might have caused this difference in the traffic graph. It was back in 2012 when Italy was playing football matches. So it always amazes me to see the hole for the first half, the peak at halftime break, and the hole for the second half. 2 years after, the very same occurred in FIFA World Cup in Brazil. You see the shape is absolutely the same. And 2 years after, again, when Italy lost against Germany, that very big hole here is when there was penalties on. And since 2018, actually, we started seeing the opposite happen. So whenever there was an important football match, the traffic actually was growing. And that is the DAZN effect. So DAZN is not a direct member of Mix, but the CDNs, the content delivery networks that carries the traffic of DAZN are connected to Mix. And that's why we see the traffic increasing. And so since then, we got used to registering new traffic peaks whenever there was an important football match in either Serie A or Champions League. And there have been other cases, and maybe some of you directly contributed to this big peak here, because it was an important release of Fortnite that got our traffic pumping up. Because again, the CDNs that are connected and that brings those updates to your consoles, for example, all the CDNs are connected to Mix. Your internet service provider is connected to Mix, and that's why we see that kind of traffic. But every now, I mean, overall, it's always football matches that brings us new traffic peaks. The current record holder is the Champions League match between Napoli and Eintracht. And this is the total amount, the total traffic, the sum of every interconnection, every interface. If we have a closer look, we can see two major groups when this happens, because we have on the left-hand side here, we have the CDNs, the subjects that pump traffic into the exchange. And on the other half, you have the access providers, so the providers that bring then traffic to your homes. And as you can see from this picture, Mix is a big pipe. Traffic comes in, traffic comes out. Nothing is injected, nothing is dropped in the middle. And another funny fact, again, when we have these football matches, the graph above is CDN, and the graph here is social network. So you see that whenever the football match starts, who cares about social network? But whenever there is the halftime break, we have to grab our phones back, and then we put them away for the second half. So you see there's actually a big chunk of traffic missing here. Everything happens in our data center. Data center, as Alberto was presenting, are crucial pieces of the puzzle. Mix has its own data center, and this is pretty much unique among the IXP's landscape. It's a space that grew over time. We ate up our office space to make space for new data center. Our data centers are certified. And as I said at the beginning, we are inside the Caldera campus because there is a surrounding of data centers similar to ours, run by other companies, but all of these data centers are connected to our data center by means of underground tunnels that physically connects the building to one another. So on these shelves here, there are literally thousands of fibers running, and whenever they reach our data center, they are organized in optical boxes. I brought a couple here so you can have a closer look afterwards. And inside the data center, the space is regulated by cabinets where routers of our members are installed, and fiber travels either under the raised floor, which is not as special as the one that Alberto was presenting before. These are regular tiles that stays there, basically. And sometimes fibers go up above our heads. Outside, the caldera is still our main pop, where the majority of traffic is being exchanged, but we have several pops throughout Italy, mainly in the surroundings of Milan. Last year, we'd opened up in Bologna. There are 2 new pops being opened this year, one in Caserta, one in Roma, where 2 new IXPs, mixed-branded IXPs, will start. We also have a point in Carini, Palermo. Why is that? Because the Mediterranean is home of several undersea cables, which are, again, another crucial part of the internet infrastructure. It's a bit bright, this slide, but you see that Italy has a geographical advantage in the Mediterranean basin. We have important cities in Sicily, so we have Palermo, Mazara del Vallo, and Catania. We have Bari in Puglia. We have other cities that are interested by undersea cables, and in the European landscape, Marseille in France is currently the most important one. Mixed together with other companies, founded OpenHubMed, which is a data center in Sicily that wants to be an important player in the market. That submarinecablemap.com is a sort of Google Maps for undersea cables, so you can zoom in, see who's the owner, and so on and so forth. I don't know if you ever saw a subsea cable. This is the shape of a subsea cable, where the actual fiber is just that tiny segment here. All the rest is mechanical protection, because the menace, the danger, the main danger to this infrastructure are made by humans. So we have fisher nets and anchors of ships. So if you ever think about a shark biting an actual cable, that really doesn't count as an important factor in damaging undersea cables. And with the shark bite, I think it's pretty theatrical way of saying thank you all. So if you have questions, of course, I'll be around here.
Okay. Thanks a lot, Simone, for your talk. There are a lot of questions, as always. We will ask the most upvoted ones,
Okay.
but anyone can then just come to you and ask for more. First, do RIRs have geopolitical leverage?
I think I would say mostly no. I mean, RIRs, most of what they do is really being a registry for internet resources. So those 5 entities have the mandate of distributing IPv4, IPv6 addresses and autonomous system numbers. They do much more in terms of activities. So, for example, RIPE-NCC organizes an event twice a year, a week-long event, which you can follow via streaming for free. They do many courses. Of course, they are somehow into politics talks, but again, only for what is related to internet
They
topics.
won't try to switch off Turkey from tomorrow.
No. They surely work for the good of the internet, generally speaking. Yeah.
How do you achieve net neutrality? Do you think that the net neutrality is in danger?
Wow, that's a pretty big one. Net neutrality has been and continues to be an important topic. We want to enforce that. We try to stay as neutral as possible whenever we take a decision. We go and open up POPs wherever we think it makes sense for the community, because we want to be there and to foster local community and local connectivity. It's not necessarily an easy job, but it's something that we really believe in.
It's mostly based on your ethic.
Yes, yeah.
Okay, got it. How do you face the peak of traffic during the pandemic?
Yeah, I had a couple of slides to actually show you, but I mean, too much, too much information. What we saw is that the traffic changed its shape because instead of having just the peak of the evening, we had 3 peaks throughout the day. So the remote learning for school at in the mornings, in the afternoons, and in the evening, we had 3 basically equal peaks throughout the day. And generally speaking, we had a 35 to 40% increase in the volume of traffic being exchanged. Mostly it happened overnight, because from when the first lockdown started, and we saw the very same things for the first and the second lockdown, exactly the same.
Got it. What happens if Caldera goes down?
Ooh. Come on, guys, easier question. That would be a massive problem. That would be a massive problem. Actually, to give a precise answer, it's not only upon us to think of replicating a Caldera somewhere else, but we can easily bring our switches whenever and wherever we think it's useful. But together with our switches, we have to convince our 400 members to replicate their network and place it somewhere else. And that's not easy to achieve. We have several POPs in Italy, and so it's good to have concentration. It's not good to have too much concentration. So the effort here is actually trying to diversificate the path, and the efforts of those data center builders that started building data centers, not just in Caldera, but outside as well, I think goes in that direction.
Clear, clear. Thank you. Is all internet in northern Italy going through a mix? Could my ISP send me to another AS without going through an IXP? And I think this is related to the fact of what are the advantages as well, also going through mix or another similar?
Okay, there are other IXPs in Italy, in addition to Mix. Mix is the largest one in terms of traffic being exchanged and number of networks being connected. So whenever a new network approaches the IXP world, it makes sense for them probably to come to Mix, because they find directly connected a much higher number of autonomous systems. The way that an internet operator manages the traffic of its customers is something that is pretty much outside our scope. So again, we have no way of forcing them to use Mix instead of another IXP. So if they are connected to another IXP and they are happy to be there because they find all the peering partners that are important to them, well, that's we can do nothing about it. The main advantage of being connected to an IXP is on a general level experiencing better performances, because your network moves closer to all the other networks that are connected to the environment, and you have much more control over your traffic when you connect to an IXP, because you are not bound to to being managed to a bigger network operator. You are directly facing all the other peering partners, so you also have to be ready in order to do that.
Got it. Question. Okay. There are many more questions, but I think the people in the crowd will ask you directly.
Absolutely. I'd be
so
more than
the
happy
last
to.
one is a funny one. So did the cameraman survive the shark?
I wasn't there, so I don't know.
Can I say? Okay, thanks a lot, Simone.
Thank
More
you.
applause.
Thank you.
We told you we would have got back here. So we are getting to that moment of the night, and now it's the messy part. No, I mean, Back in the days, it was kind of a messy moment because we were like, okay, the chairs here, the chairs there, here the yellow one, here the orange one. It is quite easy, if you notice. But first, before telling you this, there is one way that you can help Speck&Tech grow and scale and host more events. That is, first, buying our merchandising. Second, donating. The desk is there. There's Michele and Nicola waving at you, so you can just go there and leave a donation while you drink a marvelous beer. Before wrapping up the night, those of you with the yellow chairs, we take them here in this room. The orange and the black one goes at the entrance, next to the entrance door. The very big one, the very big black one, we just leave them around. And the red one, we stack them. If you are sitting on a chair that doesn't look like any of those, just stay sit on that, okay? Good night. See you next time.